All right, shifting gears. I know I've got a recording of this, and I was trying to find it before class and kept getting sidetracked. But I realized that there's a reference in the list of videos of, I strongly recommend that you watch this video, and I gave the date and with a link. And the link is probably something that doesn't work for any of you because it's to a previous semester. But I gave you hopefully enough information that you could find it. However, when I was watching the video, I noticed that it was done at a lower resolution. It's a little bit blurry, so hopefully this will be not quite as blurry, as well as something you can access more easily. The book and the mug. Book. Mug. Initial velocity, 10 meters per second, or initial speed, 10 meters per second up the ramp. We'll make that 30 degrees. Let's make the mass of the mug, I'm gonna call it power. So I'm not doing M sub M. M sub C is 0.5 kilograms, and the book, we'll make mass of book, it's a heavy one, 2 kilograms. I should say, it's a massive one. And the question is, how far will that book slide up the ramp before it stops? So let's give some sense of realism. We'll throw friction in here. So the static coefficient is, we'll make it 0.4, and the kinetic coefficient 0.3.
Dr. Fox, are you recording this?
I think so.
Your phone jammed and something about that.
This recorder.
Oh, it. It got dark because that turned off. And naturally, when the screen turns off, it should stop charging, right?
Yeah, something else came back up and it popped in. It got brighter.
Thank you. All right, so solving a problem like this, Facades method. Force diagram. I care really only about the book and the cup. We can throw other things in there if need be, but those are the things that are actually going to move. And I've simplified the cup to look like a briefcase, or purse, or
Have you thought about art school?
a rising sun. Pardon?
You should be an artist.
I know. All right, so what are the forces acting on the book? Oh,
It's the pool.
go to our checklist there at the bottom.
Weight downwards.
Okay.
On the ramp, wouldn't that be pushing up on it as well?
The
The ramp or whatever that
okay,
is.
in which direction?
Yeah, normal. force.
Pushing
Okay.
up on the box.
And the pulley. The pulley.
I didn't throw the pulley into the system there. We could if we wanted, and apparently you want to, so let's do it. We'll throw a string or the rope, and then we'll put pulley. So we got W sub B there just for completeness, and that's our angle. So what's going on with the pulley then?
Pulling off the book.
Pulley's not touching the book.
Oh, it's not, never mind.
What is the pulley touching?
The rope.
Yeah, so which way is it exerting a force on the rope?
Up.
When you say up, that's up. So up at an angle. All right, so it is pushing this way, so we got, I guess, called y sub r, and then y sub r. We apparently opened it up more than just the book, so what other forces are involved on what?
The ropes pulling on the book. That way.
What force is that called?
Other force,
Tension?
Tension.
what he said.
Assume ideal rope, ideal pulley.
Friction the other way? Of the tension, friction up the ramp?
Friction's that way? Why is friction up the ramp?
Because the boat wants to move that way, I think. Wait, it didn't. Okay, sorry. The friction is saying they like the tension.
Yeah, the book's not at rest, the book is moving at this point. So the friction is acting this way, so friction, book. Let's just sort of go down the checklist. Have we done all of the weights?
What it is. Just a cup.
What about in the problem? Yeah, okay, we got weight of cup also. And those are really the only two objects that have any mass here. This is, you know, part of the earth in my mind, so that's done. Normal forces that we have contact between book and ramp, so we got that normal force pair. We got pulley and rope, that normal force pair. That's pretty much it. There's no other. Tension, do we have all the tensions? What is the other set of tensions?
The cup.
Acting which way on the cup?
Up. Up.
And friction requires a normal force pair. These are ideal, so no friction there. And we do have already have the friction accounted for there. All right. Let's establish our coordinate, actually the acceleration. In which direction is this going to accelerate?
Down. Down.
The book's going to accelerate straight down?
Along the ramp.
Yeah, along the
Okay.
ramp there.
Okay. All right. So it will accelerate in that direction. Why is it not accelerating that way?
Because it
Because
has,
there's no action force on it in that direction.
Okay. I don't have any forces in that direction. That's a chapter 4 answer. From a chapter 2 answer, why do we know that the acceleration's got to be this way?
because there's something else pulling it down.
It's still a chapter 4.
Gravity.
Gravity.
Acceleration due to gravity.
Ultimately, we'll connect it to that, but as this book is moving up the ramp, is it speeding up or slowing down?
Slowing down.
Therefore, the acceleration has to be opposite the direction of the velocity. So that's the chapter 2 answer. Oh, by the way, if I give you a question where, you know, you can answer it with chapter 4 stuff, I'm fine with that, unless I specify. All right, so my acceleration is going to be that way. And for the cup, which way will the acceleration be?
Down.
I hope so. It's still moving upwards, but it is slowing down as it goes. So when you come up with the coordinate axes, you can come up with the coordinate axes based upon the acceleration, not a problem, then I would expect acceleration to be a positive number. Or we could set it opposite, in which case I expect acceleration to be a negative number. Let's just, it really does not matter. Let's just stick with the direction of acceleration. So I'm going to call this I sub b, j sub b, and down here, I sub c, or j sub c, whichever one you want to go with. All right, so we've done the force diagram, we figured out the acceleration, we just did the coordinate axes. What do we need to break up? What do we decompose? Does anything need to be decomposed?
The weight
Yeah.
of the book.
Well, we've done that before, so I know that I'm given the angle off the horizontal here. So I'm basically gonna take that weight, well, let's put everything else, so I got FB, FT, YB. I'm gonna take the weight, breaking that up, and I know into the ramp, it's gonna be the weight times the cosine of 30 degrees, and down the ramp, weight times the sine of 30 degrees. Equations of motion. How many equations of motion am I gonna have? 3. Right? So I'm gonna have the book and I and J.